My name is JessicaGoff, and this is my master's project about the spatial relationship between North American manatee and industrial power plants. The main objectives for this project is to first understand the spatial relationship between the manatees and the power plants. Next, learn what type of power plants are manatees clustered around. And lastly, learn about the health of the manatees observed near the power plants. And for this, I will primarily be looking at the mortality of manatees. So I'm focusing on Florida. So the Florida manatees are listed as an endangered species. The type of environment that they need to survive in is mostly found on the coastal waters of Florida. In 1991, the U.S. Fish and Wildlife began conducting aerial surveys to figure out how many manatees were in Florida. During that time, only 1,267 manatees were estimated. Today, that number has grown to 6,300. So what is the cause of the species population to increase? And could it be that industrial power plant have a part to play in it? So my process is to understand the relationship between manatees and power plants. I'm going to conduct a hotspot analysis to look at each feature that within the context of the neighboring features, and a co-location analysis where we'll look at the local patterns of spatial association in ArcGIS Pro. And then to understand the type of power plants, I will utilize the Summarize Within tool and the Spatial Join tool. And then to understand the health, I'll just use the Spatial Join tool. All the data used in this project came from the Florida Fish and Wildlife Conservation Commission and Homeland Infrastructure Foundation level database. The manatee data that I used for this project was attributed to have 1 point equal multiple observed manatees. I found this to skew my results, and therefore I needed to have my data not be dissolved, but instead exploded so that each point on the map represented one manatee. The best way I found to do this was to export the attribute table into Excel and run a code that would create new rows as many times as the value and the total number of manatees observed. Some points were 1 point would equal 1,500 manatees. And so that's one example of it skewing my data. In the hotspot analysis, I used the GI statistic to see if there's high or low clustering. The GI statistic produces the values and p-values that are then represented visually here. The hotspots with a 99% confidence has a z-value or a z-score and a high z-score and a low p-value. Cold spots obviously have the opposite. Hot or cold spots with a 99% confidence indicates that there is less than 1% chance that the clustering is at random. Areas where there are power plants, we see high clusterings like Tampa Bay, Kennedy Space Center, and Miami. For the co-location analysis, I used Model Builder to run 5 co-location analysis at different distance bands to look for patterns of spatial association between the power plants and the manatees. I decided to look at the distance bands of 2, 6, 10, 15, and 20 miles to see if there's an attraction of manatees to the power plants change. The distance bands ensures that the scale of the analysis is the same across all neighborhoods in the study area. At 2 miles, we see that manatees are co-located in a few areas like Tampa Bay and Miami, but we do see a lot of points that are isolated, not significant, which indicates that they are more likely to be random and not attracted to power plants. Here's it at 6 miles, where we see more manatee power plants that more manatee points are more likely to have power plants as in their neighborhood. Here's it at 10 miles, 15, and 20. When the distance band increases, there is more points that are significant, shown in this analysis. This shows the relationship between the local collocation coefficient and the p-values calculated. At the distance bands increases, the scatter plots get more linear. As you can see, 2 miles, 6 miles, 10 miles, 15 miles, and 20 miles. Next, we're going to look at the different types of power plant locations. Here we have a map showing the different type of power plants in Florida. It only made sense to show power plants that are within 1 mile from water. So I created a buffer to extract the power plants that fall within that criteria. Next, I did a spatial join and calculated which manatees were within a 2 nautical mile radius and created a graph to see which type of power plants were manatees clustering by. According to this data, manatees like to cluster around natural gas power plants. Those are all in green if the text is a little too small. So what do manatees need to survive? Well, they need water that is 68 degrees Fahrenheit or above, or they get, it's called cold stress, and it causes them to die. And they also need food source like seagrass. So here's maps of 3 different types of mortality. The first one is mortality by nature. This primarily is red tides are included in this. And you see that a lot of the mortality by nature are on the west side of Florida. Mortality by humans, pretty consistent all across Florida. And then mortality by cold stress is mainly on the east coast of Florida. So what do you think that is the leading type of mortality between the 3 types? Well, like nature, like red tides, tend to be highest mortality rate according to this chart. The second would be watercraft collision, and the second would be cold stress. In this graph, the majority of manatees found dead are around natural gas power plants, which makes sense because we learned previously that the manatees like to surround themselves next to natural gas power plants. So, summary, we learned that there is indeed clustering around known power plant locations. Their favorite type of power plant to cluster around is natural gas. And lastly, most mortality occurs around natural gas power plants when comparing types of power plants and mortality. And most mortality was caused by nature like red tides. Thank you.